What scares scientists more than an asteroid heading for Earth? An interstellar object that might be studging us right back. Comet 3I-ATLAS is generating mysterious emissions that suggest internal illumination. Not reflected sunlight, but something far more disturbing. Harvard's Avi Loeb calls it a potential alien probe disguised as a comet, racing through our solar system at 200,000 kilometers per hour while conducting what might be reconnaissance. The terrifying possibility isn't that we're being invaded, it's that we're being evaluated. Like lab rats under cosmic observation, humanity faces its first potential contact with superior intelligence, and we have no idea what criteria we're being judged against. Settle in as we explore the latest data and reflect on whether humanity should prepare for enlightenment or extinction. Part 1. Should we fear it? On July 1st, 2025, a telescope in Chile's Atacama Desert captured something extraordinary. A faint smudge of light moving against the star field, carrying the unmistakable signature of an interstellar traveler. This was 3I-ATLAS, also designated C/2025N1, the third confirmed visitor from beyond our solar system. But unlike the previous two interstellar objects that graced our cosmic neighborhood, 3I-ATLAS arrives at a time when social media amplifies every whisper, when speculation travels faster than light, and when the line between scientific wonder and existential dread has never been thinner. NASA assures us there's no threat. The object will never venture closer than 1.8 astronomical units from Earth. That's roughly 270 million kilometers, a comfortable distance by cosmic standards. Its closest approach to our Sun is scheduled for late October 2025, placing it just inside Mars's orbit at approximately 1.36 to 1.4 astronomical units. Yet something about this visitor feels different. Moving at over 200,000 kilometers per hour relative to our Sun, the Hubble Space Telescope and European Space Agency have declared it the fastest solar system visitor ever imaged. Its trajectory is hyperbolic, unbound by our Sun's gravitational embrace, confirming its foreign origins with mathematical certainty. Through our most powerful telescopes, we observe a dusty coma surrounding what appears to be a nucleus between 0.32 and 5.6 kilometers in diameter. The bright fuzz we see isn't the object itself, but rather a cloud of dust and gas enveloping a much smaller core. Recent spectroscopic analysis from SphereX and the James Webb Space Telescope has detected carbon dioxide and water in this environment, signatures that point toward cometary activity rather than bare rock. But here's where the story becomes complicated. Interstellar visitors are rare cosmic events, and the previous two, 1I/Oumuamua in 2017 and 2I/Borisov in 2019, ignited fierce scientific debates. Oumuamua's unusual acceleration and lack of visible outgassing led some researchers to propose it might be artificial. Borisov, thankfully, behaved like a textbook comet. Now 3I-ATLAS arrives in our era of real-time social media coverage and 24-hour news cycles where sensational headlines spread faster than peer-reviewed analysis. The central question that will guide our investigation is deceptively simple yet profoundly important. Is 3I-ATLAS a natural comet following the laws of physics? Or could some of its observed characteristics hint at something more extraordinary, perhaps even technological? The stakes of this question extend far beyond academic curiosity. If we're wrong about what's approaching our solar system, the implications could reshape our understanding of our place in the universe. We'll examine the discovery story in detail, explore the orbital peculiarities that have raised eyebrows, including its trajectory near the ecliptic plane and its precise flyby encounters with Mars and Jupiter. We'll investigate natural explanations for its behavior, consider hypotheses about potential artificial origins, and analyze how institutions respond to such extraordinary claims. The current evidence strongly supports the conclusion that 3I-ATLAS is a natural, carbon dioxide-rich comet passing safely through our solar system. Its composition, behavior, and physical characteristics all align with what we'd expect from a chunk of ancient ice and rock that has wandered the galaxy for millions of years before stumbling into our neighborhood. But science demands more than comfortable conclusions. We'll rigorously examine alternative explanations, test extraordinary hypotheses against available data, and clearly distinguish between established facts and speculative possibilities. When we encounter claims that venture into the realm of conjecture, we'll name them as such, because the difference between evidence-based analysis and wishful thinking matters more than ever in our age of information abundance. As 3I-ATLAS continues its journey toward its October encounter with our Sun, it presents us with an opportunity to examine not just the object itself, but our own responses to the unknown. How do we balance healthy scientific skepticism with openness to discovery? How do we distinguish between rational caution and paralyzing fear? And perhaps most importantly, what does our reaction to this cosmic visitor reveal about our readiness to confront the possibility that we are not alone? The universe has sent us a messenger from the stars. Whether it carries tales of ancient comets or something far more extraordinary, our response will test not just our scientific instruments, but our wisdom as a species standing at the threshold of cosmic awareness. Part 2. Discovery of a Stranger. The story of 3I-ATLAS begins not with a dramatic moment of recognition, but with the methodical patience that defines modern astronomy. The NASA-funded Asteroid Terrestrial Impact Last Alert System, ATLAS for short, operates a network of telescopes designed to scan the night sky for potentially hazardous objects. On that fateful night in July, the station at Rio Hurtado, Chile, designated W68 in astronomical catalogues, recorded what initially appeared to be just another faint moving object against the stellar backdrop. But this particular smudge of light carried secrets that would soon revolutionize our understanding of interstellar visitors. The automated systems at ATLAS dutifully logged the detection and transmitted the coordinates to the Minor Planet Center, the global clearinghouse for such discoveries. What happened next demonstrates the remarkable efficiency of our planetary defense networks. Within hours, observatories around the world were training their instruments on this mysterious newcomer. The confirmation that we were dealing with an interstellar interloper came through orbital mechanics, the mathematical language that governs how objects move through space. When astronomers calculated 3I-ATLAS's trajectory, they discovered something extraordinary. Its orbit displayed extreme hyperbolicity, with an eccentricity significantly greater than 1. In simpler terms, this object was moving so fast that our Sun's gravity could never capture it. It was clearly just passing through. The statistical significance of this conclusion is staggering. Analysis published in Astronomy and Astrophysics found that 3I-ATLAS's interstellar status could be confirmed at greater than 1700 sigma significance, a level of certainty that makes the discovery virtually undeniable. For context, particle physicists typically declare a discovery at 5 sigma. 1700 sigma is mathematical overkill of the most satisfying variety, but the story doesn't end with that July discovery. Astronomers immediately began searching through archival data, a process called precovery, to extend the observation timeline backward. They struck gold in other 3I-ATLAS telescope records and in the Zwicky Transient Facility archives, finding images of the object dating back to May 2025. This additional data tightened the orbital calculations considerably, transforming rough estimates into precise predictions. Why were scientists able to flag this as an interstellar visitor so quickly? The answer lies in the object's extreme inbound velocity and hyperbolic excess, technical terms that describe how fast it was moving relative to what our solar system could naturally produce. Objects born in our solar system are gravitationally bound to the Sun, following elliptical orbits that bring them back again and again. 3I-ATLAS, by contrast, was clearly a one-time visitor, carrying kinetic energy that spoke of journeys across the interstellar void. When first discovered, 3I-ATLAS was approximately 4.5 astronomical units from the Sun, about 675 million kilometers away, roughly the distance from the Sun to Jupiter. Its position against the star-rich galactic plane made early follow-up observations challenging, but the global astronomical community mobilized quickly. The Minor Planet Center issued circulars, NASA's Jet Propulsion Laboratory generated ephemerides, tables predicting the object's future positions, and planetary defense teams at NASA and the European Space Agency began tracking its path with characteristic precision. The object's designation tells its own story of scientific discovery. Initially tagged with the temporary identifier A11PL3Z, it quickly graduated to C/2025 N13I-ATLAS as its cometary nature became apparent. Finally, after confirming its interstellar origins, it received the historic designation 3I-ATLAS, only the third confirmed interstellar object in human history. This rapid identification process might seem routine, but it represents the culmination of decades of investment in planetary defense infrastructure. The global network that tracked 3I-ATLAS includes ground-based surveys, space-based telescopes, and sophisticated modeling systems that can predict orbital evolution with remarkable precision. Within days of discovery, astronomers knew exactly where 3I-ATLAS would be for the remainder of its solar system encounter. However, it was precisely this orbital precision that began to fuel speculation. 3I-ATLAS's trajectory, while clearly hyperbolic and unbound, exhibited one characteristic that seemed almost too convenient. Its orbit was retrograde, moving opposite to the planets, but inclined only about 5 degrees from the ecliptic plane. This meant it was traveling in rough alignment with the planetary orbits, a geometry that some observers found suspiciously orderly for a random interstellar traveler. The early days following discovery were marked by wildly varying estimates of the object's size and brightness. This uncertainty is completely normal for newly discovered comets at great distances, where instrumental limitations and atmospheric effects can produce conflicting measurements. But in our hyperconnected age, this scientific uncertainty became fertile ground for speculation. Every revision of estimates, every new observation that refined previous conclusions, was scrutinized for hidden significance. What remained constant throughout this early period was the reassuring assessment from NASA's Planetary Defense Coordination Office. 3I-ATLAS posed no threat to Earth. No early tracking suggested any possibility of impact, and the object's trajectory would carry it safely past our planet at a comfortable distance. For the planetary defense community, 3I-ATLAS was simply another cosmic visitor to catalogue and study, albeit a particularly fast and interesting one. Yet even as astronomers worked to understand this new arrival, something about its behavior continued to intrigue and occasionally unsettle observers. The combination of its high velocity, near-ecliptic trajectory, and the timing of its close encounters with Mars and Jupiter seemed to suggest a level of cosmic choreography that challenged purely random explanations. As we'll discover, distinguishing between meaningful patterns and cosmic coincidences would become one of the central challenges in understanding what 3I-ATLAS truly represents. Part 3. A visitor out of place, brightness, size puzzles. When astronomers attempt to determine the size of a distant object, they're essentially playing cosmic detective with limited clues. For most asteroids and comets, we infer size by measuring reflected sunlight, making assumptions about surface reflectivity, what scientists call albedo, and accounting for any surrounding dust or gas clouds. With active comets like 3I-ATLAS, this process becomes significantly more complicated because the glowing coma often dominates the total brightness, effectively hiding the nucleus from direct observation. The Hubble Space Telescope's observations of 3I-ATLAS provided our first reliable constraints on the object's true size. After careful analysis that accounted for the surrounding dust cloud, astronomers concluded that the nucleus, the actual solid body at the heart of the comet, measures between 0.32 and 5.6 kilometers in diameter. These might seem like loose constraints, but they represent the cutting edge of what's possible when studying such distant objects. Early reports from various observatories describe something particularly intriguing: an apparent forward glow, or sunward plume extending from the object. In the language of cometary science, this is sometimes called an anti-tail, a phenomenon that occurs when dust particles are pushed around by solar radiation pressure and orbital mechanics, creating the illusion of material flowing toward the Sun rather than away from it. For 3I-ATLAS, Hubble's high-resolution imaging revealed a teardrop-shaped dust cocoon surrounding the hidden nucleus, a morphology that fits perfectly with classical cometary behavior. But it was spectroscopic observations that truly began to unlock 3I-ATLAS's secrets. The PHEREX mission detected an extended carbon dioxide cloud, measuring at least 348,000 kilometers across, roughly equivalent to the distance between Earth and the Moon. This enormous carbon dioxide coma provided the first definitive evidence that 3I-ATLAS was actively outgassing, sublimating frozen carbon dioxide directly from its surface into space as it warmed in the Sun's radiation. The James Webb Space Telescope added another crucial piece to this puzzle. On August 6, 2025, JWST's near-infrared spectrograph obtained spatially resolved spectra of the object, essentially creating a detailed chemical map of different regions within the coma. The preliminary results showed clear carbon dioxide features, confirming PHEREX's detection with independent measurements. However, as with all cutting-edge science, these interpretations remain subject to peer review and further analysis. This brings us to what some observers have termed the brightness anomaly surrounding 3I-ATLAS. Several early reports suggested that the object's brightness appeared oddly concentrated on the sunward side, leading to speculation about possible self-illumination or other exotic phenomena. However, experienced comet researchers quickly recognized this as a likely example of dust phase angle effects, a well-understood optical phenomenon that can make cometary dust clouds appear brighter when viewed from certain angles relative to the sunday. The appearance of sunward-pointing anti-tails is actually quite common in comets and results from the complex interplay between solar radiation pressure, particle sizes, and viewing geometry. Large dust grains, too heavy to be easily blown away by solar wind, can create extended structures that appear to point toward the Sun when viewed from specific perspectives. There's nothing mysterious or artificial about this behavior, it's simply physics in action. One persistent source of confusion in media coverage has been the conflation of coma size with nucleus size. Some early reports claimed 3I-ATLAS measured tens of kilometers across, but these measurements almost certainly described the extent of the dust and gas cloud, rather than the solid nucleus itself. The Hubble constraints make clear that the actual object is relatively small, a few kilometers at most, surrounded by an enormous cloud of sublimating gases and dust. The detection of both carbon dioxide and water vapor in 3I-ATLAS's environment strongly supports the natural comet hypothesis. Carbon dioxide sublimates at much colder temperatures than water ice, which explains why it dominates the coma at 3I-ATLAS's current distance from the sunday. As the object approaches perihelion in late October, we should expect to see water vapor signatures become more prominent as surface temperatures rise sufficiently to sublimate water ice. This volatile composition tells a fascinating story about 3I-ATLAS's probable origins and history. The presence of significant carbon dioxide suggests the object formed in a very cold environment, exactly what we'd expect for a body that spent millions of years wandering the interstellar void. During this long journey, cosmic rays would have bombarded the surface, potentially altering the chemical composition and creating the volatile rich surface we observe today. Some researchers have attempted to trace 3I-ATLAS's origin story by analyzing its trajectory and composition. Different teams have suggested it might have originated from the galaxy's thin disk or thick disk, regions with different stellar populations and chemical compositions. However, these models remain highly uncertain, and the true origin of 3I-ATLAS may forever remain a mystery. The photometric behavior of 3I-ATLAS, how its brightness changes over time and at different wavelengths, provides additional evidence for natural cometary processes. The measured brightness variations match what we'd expect from a rotating, sublimating nucleus surrounded by an active dust coma. There are no observations of unexplained brightness, spikes, structured thermal emissions, or other phenomena that might suggest artificial origins. As we continue to monitor 3I-ATLAS's approach toward perihelion, each new observation adds to our understanding of this remarkable visitor. The combination of gas detections, dust morphology, and brightness behavior creates a consistent picture of an active comet carrying volatile ices that were processed during its long interstellar journey. Yet questions remain. The exact composition of those ices, the internal structure of the nucleus, and the detailed mechanisms driving the observed outgassing all await further investigation. 3I-ATLAS may look like a straightforward comet, but its status as an interstellar visitor makes every aspect of its behavior scientifically precious. The bottom line from current observations is clear. What we're seeing appears to be the result of active comet physics rather than technology. But as any good scientist knows, appearances can sometimes deceive, and extraordinary claims require extraordinary evidence to either support or refute them. Part 4. The Alien Technology Hypothesis. In the realm of scientific inquiry, few researchers are as willing to venture into controversial territory as Dr. Avi Loeb, the Frank B. Baird Jr. Professor of Science at Harvard University and founding director of the Black Hole Initiative. When it comes to 3I-ATLAS, Loeb and his collaborators have raised a provocative possibility that deserves serious examination, even if it challenges conventional astronomical thinking. Could this interstellar visitor be artificial rather than natural? Loeb's argument rests on several observational features that he considers potentially compatible with technology. The apparent sun-facing glow observed in early reports, the object's trajectory that brings it remarkably close to the ecliptic plane, and its precisely timed flyby encounters with Mars and Jupiter all represent, in his view, patterns that merit investigation beyond purely natural explanations. Perhaps most intriguingly, Loeb has proposed what he calls a reverse Oberth maneuver scenario. In conventional spaceflight, the Oberth effect allows spacecraft to gain maximum velocity by firing engines when orbital speed is highest, typically at perihelion, the closest approach to the Sunday. A sufficiently advanced civilization, Loeb suggests, might employ the opposite strategy, using the perihelion passage to brake and decelerate by expending thrust precisely when orbital dynamics would make such maneuvers most efficient. This concept extends into even more speculative territory with Loeb's discussion of potential mothership and mini-probe configurations. The idea suggests that what we observe as 3I-ATLAS might represent either a reconnaissance probe dispatched by a larger vessel, or perhaps a fragment of an interstellar craft that has broken apart during its long journey between the stars. While these concepts remain purely theoretical, they represent the kind of thinking required to explore all possibilities when faced with unusual phenomena. Loeb has also publicly advocated for using existing spacecraft to obtain closer observations of 3I-ATLAS during its Mars encounter in October 2025 or its Jupiter flyby in March 2026. The Juno spacecraft, currently in orbit around Jupiter, might theoretically be repositioned to capture higher resolution images during 3I-ATLAS's passage. Similarly, various Mars orbiters could potentially be retasked for closer study. However, the feasibility of such observations remains uncertain, given the complex orbital mechanics and mission constraints involved. The most provocative aspect of Loeb's hypothesis concerns the possibility of self-illumination. He has suggested that the apparent brightness anomalies observed in 3I-ATLAS might indicate some form of artificial lighting or even nuclear-powered propulsion systems. This would represent a dramatic departure from natural cometary behavior, where brightness variations typically result from reflected sunlight and thermal emission from heated dust and gas. To understand these ideas properly, we must place them in the context of Loeb's previous work on interstellar objects. Following the discovery of Oumuamua in 2017, Loeb co-authored papers proposing that the object's unusual acceleration and lack of visible outgassing might be explained by a light sail, essentially a thin artificial membrane designed to be pushed by stellar radiation. While most researchers have since concluded that natural outgassing of hydrogen gas can explain Oumuamua's behavior, the light sail hypothesis sparked important discussions about how we might recognize artificial objects in space. The scientific community's response to these technological hypotheses has been mixed but generally skeptical. Most astronomical observations of 3I-ATLAS support conventional cometry interpretations, the detection of carbon dioxide and water vapor, the presence of a substantial dust coma, and the morphological characteristics observed by Hubble all fit naturally with expectations for an active comet. This brings us to a fundamental principle of scientific inquiry. Extraordinary claims require extraordinary evidence. While technological explanations for 3I-ATLAS's behavior remain theoretically possible, no observations to date have detected the kinds of signatures we might expect from artificial objects. No structured radio emissions, no engineered materials in spectroscopic analysis, no geometric features in high-resolution imaging, no signs of controlled propulsion or navigation. Yet Loeb's willingness to propose these ideas serves an important function in the scientific process. Hypotheses, even speculative ones, help guide observations by suggesting what kinds of evidence we should look for. If 3I-ATLAS were indeed artificial, what specific signatures should we expect? How would its thermal emissions differ from natural outgassing? What kinds of spectral features might reveal manufactured materials or controlled energy sources? The exploration of these possibilities also forces us to confront a deeper question about our assumptions. As we search for life and intelligence beyond Earth, how would we recognize truly alien technology? Would it necessarily conform to our expectations based on human engineering principles? Or might advanced civilizations develop technologies so sophisticated that they're virtually indistinguishable from natural phenomena? For now, the balance of evidence strongly favors natural explanations for 3I-ATLAS's behavior. The carbon dioxide detections from SphereX and JWST, the dust morphology revealed by Hubble, and the overall behavioral patterns all align with established cometry physics. No current observations require invoking artificial origins to explain what we see. However, science progresses through the testing of alternative hypotheses, and Loeb's technological scenarios provide valuable frameworks for evaluating future observations. As 3I-ATLAS approaches its close encounters with Mars and Jupiter, we'll have opportunities to conduct more detailed observations that could either support or definitively rule out artificial explanations. The key is maintaining appropriate scientific skepticism while remaining open to unexpected discoveries. We should neither dismiss unconventional ideas without proper investigation, nor accept them without compelling evidence. In the case of 3I-ATLAS, this means continuing to monitor the object carefully, searching for any anomalous signatures that might support technological hypotheses, while remaining grounded in the substantial evidence for natural cometry activity. Whether 3I-ATLAS proves to be an exotic comet or something far more extraordinary, our investigation of both possibilities exemplifies science at its best, rigorous, open-minded, and committed to following the evidence wherever it leads. Part 5. The Case for a Natural Comet. The scientific method thrives on building cases from multiple independent lines of evidence, and when it comes to understanding 3I-ATLAS's true nature, the natural comet hypothesis enjoys substantial support from observations across the electromagnetic spectrum. Each piece of evidence, examined individually, points toward conventional physics. Taken together, they construct a compelling argument for 3I-ATLAS as a remarkable but ultimately natural visitor from interstellar space. The most direct evidence comes from gas detections in 3I-ATLAS's immediate environment. SphereX's identification of an extensive carbon dioxide coma spanning at least 348,000 kilometers provides unambiguous proof of active sublimation. The the direct transition of solid carbon dioxide ice to gas as solar radiation warms the object's surface. This process is fundamental to cometary physics and requires no exotic explanations. The James Webb Space Telescope's detection of carbon dioxide features through spatially resolved spectroscopy adds crucial confirmation to these findings. JWST's unprecedented infrared sensitivity allows it to identify molecular signatures with remarkable precision, and the preliminary results show exactly what we'd expect from a carbon dioxide-rich comet at 3I-ATLAS's current distance from the Sun. Equally important is the morphological evidence provided by Hubble Space Telescope observations. The high-resolution images reveal a classic teardrop-shaped dust cocoon surrounding an unseen nucleus, a structure that matches theoretical models of cometary activity with extraordinary fidelity. There are no geometric irregularities, no engineered features, no structural elements that suggest artificial construction. Instead, we see the elegant simplicity of physics in action, a small, cold object warming in stellar radiation and releasing stored volatiles into space. The size constraints derived from Hubble observations, a nucleus diameter between 0.32 and 5.6 kilometers, align perfectly with expectations for interstellar comets. Objects in this size range have sufficient mass to retain volatile ices during long interstellar journeys, yet remain small enough that solar heating can drive significant outgassing activity when they encounter a stellar system. 3I-ATLAS's extreme velocity and hyperbolic trajectory, while unusual by solar system standards, make perfect sense for an object that has wandered interstellar space for millions of years. Computer simulations of galactic dynamics show that objects ejected from other stellar systems will accumulate random velocities through gravitational encounters with stars, molecular clouds, and other galactic structures. An object with 3I-ATLAS's speed and trajectory fits naturally within this population of interstellar wanderers. Perhaps most importantly, we can compare 3I-ATLAS directly to 2I/Borisov, the previous interstellar comet discovered in 2019. Borisov exhibited exemplary cometary behavior, showing clear transitions from carbon monoxide and carbon dioxide dominance at large distances to water vapor dominance as it approached perihelion. The compositional similarities between 3I-ATLAS and Borisov suggest we're dealing with the same class of objects, chunks of primordial ice and rock that formed around other stars billions of years ago. The international monitoring campaign studying 3I-ATLAS represents a triumph of collaborative science. Hubble provides size constraints and morphological analysis. JWST contributes detailed spectroscopic identification of molecular species. SphereX maps the extended coma structure. Ground-based telescopes like the Gran Telescopio Canarias contribute photometric and compositional analysis while continuously refining orbital predictions. Each instrument answers different questions, and their combined results paint a consistent picture of active cometary processes. One persistent source of confusion in media coverage has been the misinterpretation of size measurements. Some reports have described 3I-ATLAS as dozens of kilometers across, but these measurements almost certainly refer to the extent of the dust and gas coma rather than the solid nucleus. The Hubble Space Telescope's careful analysis, which accounts for coma contributions to the total brightness, provides much tighter constraints on the actual object size. The question of 3I-ATLAS's ultimate origin remains scientifically fascinating but uncertain. Different research teams have proposed origins in either the galaxy's thin disk or thick disk, regions characterized by different stellar populations, ages, and chemical compositions. Some models suggest 3I-ATLAS could be older than our solar system itself, a relic from the galaxy's early epochs of star formation. However, these origin models carry substantial uncertainties, and the true birthplace of 3I-ATLAS may never be definitively determined. The close approaches to Mars and Jupiter that have attracted attention in some circles are actually less remarkable than they might initially appear. Statistical analysis of hyperbolic orbits shows that many random interstellar trajectories will experience close encounters with major planets simply by chance. The fact that 3I-ATLAS passes within 0.19 to 0.20 astronomical units of Mars and 0.36 astronomical units of Jupiter says more about the size and gravitational influence of these planets than about any intentional targeting. Current monitoring efforts continue to support the natural comet interpretation. Photometric observations show brightness variations consistent with a rotating, sublimating nucleus. Spectroscopic monitoring detects exactly the molecular species we'd expect from warming cometary ices. Morphological studies reveal dust structures that match computational models of cometary activity. No observations require invoking exotic physics or artificial origins. As 3I-ATLAS approaches its late October perihelion, we can make specific predictions based on the natural comet hypothesis. Water vapor signatures should become more prominent as surface temperatures rise above the sublimation threshold for water ice. The dust production rate should increase, potentially making the coma more visible to ground-based observers. The nucleus may begin to show signs of fragmentation if thermal stresses exceed its structural integrity. These predictions are testable and specific, providing clear ways to validate or challenge the natural comet interpretation. If 3I-ATLAS were artificial, we might expect very different behavior: stable brightness unrelated to solar distance, absence of volatile signatures, or geometric features visible in high-resolution imaging. For now, the scientific consensus strongly supports treating 3I-ATLAS as a natural, if remarkable, example of an interstellar comet. Its carbon dioxide-rich composition provides insights into conditions around other stellar systems billions of years ago. Its successful preservation of volatile ices during interstellar travel illuminates the physics of small body evolution in the galactic environment. Whether 3I-ATLAS ultimately proves to be an exotic natural object or reveals unexpected anomalies, our careful study of this visitor exemplifies science at its most fundamental level. The patient accumulation of evidence, the testing of competing hypotheses, and the willingness to be surprised by what the universe reveals. Part 6. The Fear Instinct. To understand why 3I-ATLAS has generated such intense interest and occasional anxiety, we must examine the peculiar psychology that governs human responses to cosmic events. Our brains, evolved over millions of years to navigate terrestrial dangers, display systematic biases when confronting the infinite scales and alien physics of space. These biases shape not just individual reactions, but the collective conversations that emerge around mysterious celestial visitors. Psychologists have identified a phenomenon known as dread risk, our tendency to overweight the probability and severity of catastrophic but low likelihood events. This mental shortcut served our ancestors well when estimating threats from predators or natural disasters, but it creates systematic distortions when applied to astronomical phenomena. A comet that poses zero actual danger can still trigger intense anxiety simply because it represents an unknown quantity from an incomprehensibly vast universe. The affect heuristic compounds this problem by linking our emotional responses directly to our risk assessments. Events that feel frightening are automatically judged as more dangerous, regardless of objective evidence. When confronted with something as alien as an interstellar visitor traveling at 200,000 kilometers per hour, our emotional systems activate long before rational analysis can provide reassurance. Ambiguity serves as another powerful amplifier of fear. During the early weeks following 3I-ATLAS's discovery, when orbital parameters remained uncertain and spectroscopic analysis was still incomplete, the absence of definitive information created a vacuum that speculation rushed to fill. Humans evolved in environments where unknown threats could prove deadly, so our default response to ambiguity is heightened vigilance rather than patient curiosity. Modern media ecosystems can transform these individual psychological tendencies into collective phenomena. The 24-hour news cycle demands constant content, and uncertainty about cosmic visitors provides fertile ground for sensational narratives. Headlines emphasizing mystery, speed, and unknown origins capture attention far more effectively than measured discussions of orbital mechanics and spectroscopic analysis. We can observe this pattern clearly by comparing media coverage of 3I-ATLAS with official communications from NASA and the European Space Agency. Where headlines emphasize terms like mystery object, blazing speed, and unknown visitor, scientific institutions focus on specific measurements, distances, velocities, chemical compositions, and trajectory predictions. The same factual information generates completely different emotional responses depending on how it's framed. The precedent of 1I/Oumuamua illustrates how these dynamics can evolve over time. Initial observations revealed an object with unusual properties, an elongated shape, no visible coma, and slight acceleration that couldn't be explained by gravity alone. In the absence of immediate explanations, speculation flourished, including hypotheses about artificial origins. Only after months of careful analysis did the scientific community converge on natural explanations involving hydrogen outgassing from processed water ice. Understanding these psychological patterns helps explain why planetary defense communications emphasize concrete, measurable facts rather than interpretative speculation. When NASA announces that 3I-ATLAS will pass no closer than 1.8 astronomical units from Earth, this specific distance measurement serves multiple functions. It provides precise information for scientific analysis, it offers concrete reassurance about safety, and it demonstrates the accuracy and reliability of our tracking systems. Interviews with psychologists specializing in existential threat perception reveal fascinating insights about why cosmic visitors trigger such profound responses. These objects activate what researchers call archetypal fears, deep, culturally embedded anxieties about invasion, judgment, and cosmic insignificance that appear across human societies. The mere possibility that we might not be alone in the universe challenges fundamental assumptions about our place in creation. Yet, focusing exclusively on fear misses a crucial counterpoint: the capacity for wonder that cosmic discoveries can inspire. The same psychological systems that generate anxiety about unknown threats can also produce awe at the magnificent scales and elegant physics revealed by interstellar visitors. 3I-ATLAS offers an opportunity to witness material from another stellar system, to study chemistry that formed billions of years ago around distant suns, to glimpse the cosmic processes that shape our galaxy. This capacity for wonder serves important functions beyond mere emotional satisfaction. Scientific literacy and public support for space exploration correlate strongly with feelings of cosmic curiosity rather than cosmic dread. When people view astronomical discoveries as opportunities for learning rather than sources of threat, they're more likely to support the research programs that expand our understanding of the universe. The global collaboration required to study objects like 3I-ATLAS demonstrates humanity at its collective best. Within hours of discovery, observatories on multiple continents were sharing data, coordinating observations, and building comprehensive models of the object's trajectory and composition. This response showcases not just our technical capabilities, but our species' remarkable capacity for cooperation when confronted with cosmic mysteries. We can apply these insights to develop better approaches for communicating about future astronomical discoveries. Media literacy becomes crucial. Learning to distinguish between peer-reviewed scientific analysis and preliminary speculation, understanding the difference between uncertainty and danger, recognizing how framing effects shape our emotional responses to information. The risk assessment for 3I-ATLAS illustrates these principles perfectly. When we compare the actual risk posed by this interstellar visitor, essentially zero, with known impact hazards from solar system objects, we see that our attention and concern are dramatically misaligned with actual probabilities. NASA's Planetary Defense Coordination Office tracks thousands of near-Earth objects that pose far greater statistical risks than any interstellar visitor, yet these mundane solar system residents generate far less public interest. Perhaps most importantly, we can recognize how our initial emotional responses to cosmic discoveries need not determine our final judgments. Fear narrows our perspective, encouraging us to focus on threats and worst-case scenarios. Wonder expands our perspective, inviting us to explore possibilities and appreciate the magnificent complexity of the universe we inhabit. 3I-ATLAS invites both responses, but ultimately rewards the latter. Whether it proves to be an exotic natural comet or reveals unexpected properties, this visitor offers humanity an opportunity to demonstrate scientific maturity, the ability to face the unknown with curiosity rather than dread, to seek understanding rather than retreat into comfortable assumptions. As we continue monitoring 3I-ATLAS's journey through our solar system, we're not just studying an astronomical object, we're conducting an experiment in how our species responds to contact with the truly alien. The results of that experiment will shape not just our understanding of this particular visitor, but our preparedness for the cosmic discoveries that await us in the decades ahead. Part 7. Ancient Omens, Modern Parallels. Long before telescopes revealed the true nature of comets, human civilizations watched the skies with mixture of awe and terror. These unexpected visitors, appearing suddenly against the familiar backdrop of stars, challenged ancient assumptions about celestial order and divine intentions. The Chinese called them broom stars, believing they swept away dynasties and heralded political upheaval. Imperial astronomers meticulously recorded their appearances, creating records that modern scientists now use to reconstruct historical orbital patterns with remarkable precision. The most famous example of cometary fear embedded in human culture appears in the Bayeux Tapestry, where Halley's comet blazes across the sky above terrified English nobles in 1066. The chroniclers depicted armed men pointing at the celestial visitor with expressions of horror, interpreting its appearance as divine judgment against King Harold's claim to the English throne. For the Norman invaders, however, the same comet represented favorable divine intervention, a sign that God blessed William the Conqueror's campaign. This dual interpretation reveals something profound about human psychology. We tend to see cosmic events as confirmations of our existing beliefs and fears, rather than as independent natural phenomena. The comet itself remained unchanged, following the same gravitational laws that govern all celestial mechanics. Only human interpretation transformed it into either harbinger of doom or herald of victory. Indigenous Australian Aboriginal communities developed rich traditions around cometary appearances that varied significantly between different groups and regions. Many cultures associated these visitors with death or malevolent spirits, viewing them as tears in the sky, fabric, or signals of impending catastrophe. The Wardaman people of the Northern Territory described some comets as ancestral spirits traveling between sacred sites, while other groups interpreted them as warnings about violations of traditional law or environmental imbalance. These diverse cultural responses illuminate why fear scripts activate so readily when strange objects appear in our skies. Across vastly different societies and historical periods, humans consistently interpreted unexpected celestial events as meaningful rather than random, as signs requiring interpretation rather than phenomena demanding investigation. This pattern suggests deep psychological roots that extend far beyond rational threat assessment. The mechanism by which cometary omens spread through ancient societies bears striking resemblance to how astronomical discoveries propagate through modern social media. In medieval Europe, news of celestial apparitions traveled along trade routes and through religious networks, often arriving weeks or months after the initial sighting. By the time information reached distant communities, it had been filtered through multiple interpretations, embellished with local meanings, and merged with existing folklore. Today's digital networks accelerate this process exponentially, while preserving its essential character. A telescope in Chile detects an unusual object, and within hours, speculation about its nature spreads across continents faster than scientific analysis can provide definitive answers. The same psychological drives that led medieval chroniclers to interpret comets as divine messages now manifest as viral theories about alien technology or cosmic threats. The printing press revolutionized how comet panic could spread, but it also began to introduce corrective mechanisms. Multiple sources could be compared, authorities could be questioned, and alternative interpretations could compete for public attention. The rise of scientific institutions like the Royal Society created new frameworks for evaluating celestial phenomena based on observation rather than tradition or authority. Modern institutions attempt to fulfill similar stabilizing roles. The International Astronomical Union, NASA, and the European Space Agency provide authoritative sources for astronomical information, using standardized communication protocols designed to minimize misunderstanding and panic. When these organizations announce that 3I-ATLAS poses no threat to Earth, they're drawing on centuries of hard-won experience in distinguishing between genuine hazards and merely unusual phenomena. Yet the underlying human tendency to fill uncertainty gaps with dramatic narratives remains as powerful as ever. In the absence of complete information, and complete information about cosmic visitors takes months or years to develop, our minds default to pattern-seeking behaviors that served our ancestors well in terrestrial environments, but can lead us astray when applied to astronomical scales. The historical record reveals that comet panics follow predictable patterns regardless of the specific cultural context. Initial sightings generate uncertainty and speculation. Authorities attempt to provide reassuring explanations while acknowledging unknowns. Popular imagination fills those unknowns with culturally relevant fears: divine punishment in religious societies, foreign invasion during periods of political instability, technological threats in our current era of rapid scientific advancement. What makes our current situation both more challenging and more hopeful than previous eras is the democratization of information access. Anyone with internet connectivity can examine the same orbital data, spectroscopic measurements, and imaging results that professional astronomers use to study 3I-ATLAS. The Minor Planet Centers database, NASA's Solar System Dynamics website, and observatory press releases provide unprecedented transparency about the discovery and analysis process. This access creates opportunities for genuine scientific literacy that medieval peasants or even educated nobility could never have imagined. Citizens can learn to distinguish between preliminary observations and peer-reviewed conclusions, understand the difference between scientific uncertainty and genuine danger, and participate in the collective process of making sense of cosmic discoveries. The enduring human pattern across all these historical examples is our tendency to transform astronomical events into stories about ourselves. Ancient Chinese astronomers saw comets as reflections of imperial virtue or corruption. Medieval Europeans interpreted them through frameworks of Christian theology and feudal politics. We view 3I-ATLAS through lenses shaped by science fiction narratives about alien contact and existential risks to human civilization. This pattern isn't necessarily problematic. Stories help us process experiences that exceed our normal conceptual frameworks. The key is learning to hold these stories lightly, as provisional interpretations rather than definitive truths, and to remain open to revision as evidence accumulates. Perhaps the most encouraging aspect of our modern approach to cosmic visitors is the speed with which international collaboration emerges. Within days of 3I-ATLAS's discovery, observatories worldwide were sharing data, coordinating observations, and building comprehensive models. This response demonstrates our species' remarkable capacity for cooperation when confronted with genuinely cosmic scales and timelines that dwarf terrestrial political divisions. 3I-ATLAS represents a modern test of these ancient patterns. Will we succumb to the same fear-driven narratives that transformed every historical comet into an omen of catastrophe? Or can we develop new cultural scripts that embrace cosmic visitors as opportunities for wonder, learning, and international collaboration? The answer to that question will be written not in the stars but in our collective response to the stranger currently racing through our solar system at unprecedented velocity, carrying secrets from distant suns and challenging us to transcend the limitations of our evolved psychology. As we'll discover, we're not the first civilization to face such tests, and the precedents of Oumuamua and Borisov offer both cautionary tales and reasons for optimism about our capacity to respond wisely to cosmic mysteries. Part 8. Precedents. Oumuamua, Borisov. Before 3I-ATLAS captured our attention with its remarkable speed and carbon dioxide emissions, two previous interstellar visitors provided crucial lessons about how such objects behave and how humans respond to them. 1I/Oumuamua, discovered in 2017, and 2I/Borisov, found in 2019, established the baseline for our understanding of interstellar objects while demonstrating the importance of careful, patient analysis in distinguishing between genuinely anomalous phenomena and merely unfamiliar physics. Oumuamua arrived first, and it immediately challenged expectations about what interstellar visitors should look like. Initial observations revealed an object with an extremely elongated shape, roughly 10 times longer than it was wide, and an unusual tumbling rotation that suggested either a highly irregular form or perhaps a flat, pancake-like geometry. Most puzzling, Oumuamua showed no visible coma or tail despite exhibiting a small but measurable non-gravitational acceleration as it departed the inner solar system. This combination of properties sparked intense scientific debate and, inevitably, speculation about artificial origins. The absence of visible outgassing seemed to rule out conventional cometary explanations for the acceleration, leading some researchers to propose that Oumuamua might represent a fragment of alien technology, perhaps a light sail designed to be pushed by stellar radiation pressure, or debris from some unimaginably ancient spacecraft. Dr. Avi Loeb, whose hypotheses about 3I-ATLAS we examined earlier, co-authored influential papers proposing the light sail hypothesis as a scientifically viable explanation for Oumuamua's properties. This wasn't wild speculation but careful analysis. If an object shows acceleration without visible mass loss, and if that acceleration follows patterns consistent with radiation pressure, then artificial origins become a legitimate scientific hypothesis worth investigating. However, the scientific community's response to extraordinary claims followed predictable patterns: extraordinary skepticism. Multiple research teams worked to develop natural explanations for Oumuamua's behavior, focusing particularly on the possibility of invisible outgassing that might escape detection by telescopic observations. The breakthrough came through detailed modeling of how interstellar radiation affects the composition of small objects over millions of years. Cosmic rays and stellar ultraviolet radiation can break down water ice molecules, creating trapped hydrogen gas within the object's interior. When such an object approaches a star, the warming surface can release this hydrogen in quantities too small to create visible cometary activity, but sufficient to produce measurable acceleration. Recent analysis published in Nature strongly supports this hydrogen outgassing model, providing a natural explanation for all of Oumuamua's unusual properties. The elongated shape might result from tidal forces during close stellar encounters. The unusual rotation could reflect complex torques from asymmetric outgassing, and the invisible acceleration fits perfectly with hydrogen emission rates predicted by radiolysis models. 2I/Borisov, discovered by amateur astronomer Gennady Borisov at his personal observatory in Crimea, provided a completely different template for interstellar behavior. From the moment of discovery, Borisov exhibited textbook cometary properties: a prominent dust coma, clear evidence of outgassing, and spectroscopic signatures that revealed familiar volatile compounds. As Borisov approached its perihelion in late 2019, detailed spectroscopic monitoring revealed a fascinating compositional evolution. At large distances from the Sun, carbon monoxide and carbon dioxide dominated the outgassing, exactly as predicted by sublimation physics for objects in extremely cold environments. As solar heating intensified, water vapor began to dominate the spectrum, following patterns identical to those observed in solar system comets. The nucleus of Borisov proved to be relatively small, probably less than 1 kilometer in diameter, yet it produced dramatic cometary activity that made it easily visible to ground-based telescopes. Mass loss rates measured throughout its solar system passage matched theoretical predictions for objects with high volatile content, confirming that interstellar comets can preserve substantial ice reservoirs during their long journeys between stars. Perhaps most importantly, Borisov's behavior demonstrated that interstellar objects need not be exotic or mysterious. This visitor behaved exactly like comets formed in our own solar system, suggesting that the basic physics of planet formation, the accretion of ice and rock in cold, distant regions around young stars, operates similarly throughout the galaxy. The key lesson from comparing Oumuamua and Borisov is that interstellar objects don't constitute a single category with predictable properties. Some, like Borisov, represent familiar physics operating in unfamiliar contexts. Others, like Oumuamua, challenge our understanding and require years of careful analysis to explain through natural processes. 3I-ATLAS, with its prominent carbon dioxide emissions and substantial dust coma, initially appears much closer to the Borisov template than the Oumuamua enigma. The PHEREX and James Webb Space Telescope detections of volatile outgassing provide immediate evidence for active cometary processes, while Hubble's morphological observations reveal classical dust cocoon structures. However, the speed of 3I-ATLAS, significantly higher than either previous interstellar visitor, and its trajectory that brings it unusually close to planetary orbits, add elements of mystery that require careful investigation. We've learned from Oumuamua that unusual properties don't automatically imply artificial origins, but they do demand thorough analysis before we can confidently rule out exotic explanations. The technological advances since 2017 have dramatically improved our ability to study interstellar visitors. When Oumuamua appeared, the James Webb Space Telescope hadn't yet launched, and PHEREX remained in development. Ground-based spectroscopy provided limited compositional information, and even Hubble's observations were constrained by the object's small size and rapid motion. Today's suite of instruments, Hubble for morphological analysis, JWST for detailed spectroscopy, PHEREX for extended coma mapping, and increasingly sophisticated ground-based facilities, provides unprecedented capability for real-time analysis of visiting objects. We can detect molecular species that would have been invisible to previous generations of telescopes, map spatial distributions of gas and dust with remarkable precision, and track compositional changes as objects evolve throughout their solar system passage. This enhanced capability makes the early days of 3I-ATLAS's approach particularly exciting from a scientific perspective. Instead of waiting months or years for definitive analysis, we can build comprehensive models of composition, structure, and behavior within weeks of discovery. The importance of rapid follow-up cannot be overstated. Interstellar visitors are temporary phenomena, typically visible for only a few months before disappearing back into the cosmic void. Oumuamua had already passed perihelion by the time astronomers recognized its interstellar origins, limiting opportunities for detailed study. With 3I-ATLAS, we have the luxury of monitoring its approach, perihelion passage, and departure in real time. Future survey systems, particularly the Vera Rubin Observatory's Legacy Survey of Space and Time, promise to revolutionize interstellar object science by detecting dozens or potentially hundreds of such visitors each year. This statistical sample will allow us to understand the typical properties and behaviors of interstellar populations, making individual oddballs like Oumuamua seem less mysterious and potentially artificial. The comparative timeline of all three interstellar visitors reveals important patterns. Discovery typically occurs months before perihelion, providing time for intensive observation campaigns. Peak activity and visibility coincide with closest solar approach, when thermal heating drives maximum outgassing and dust production. Post-perihelion observations become increasingly difficult as objects recede and fade, emphasizing the importance of comprehensive early study. 3I-ATLAS's upcoming close encounters with Mars in October 2025 and Jupiter in March 2026 offer unique opportunities that neither Oumuamua nor Borisov provided. Spacecraft already in orbit around these planets could potentially be retasked for closer observations, providing unprecedented resolution and detail about an interstellar visitor's properties. Whether such observations prove feasible remains an open question involving complex orbital mechanics, mission constraints, and resource allocation. But the mere possibility illustrates how our capability to study cosmic visitors continues to evolve, building on lessons learned from each previous encounter. As 3I-ATLAS continues its approach toward perihelion, we carry with us the accumulated wisdom from Oumuamua and Borisov, patience in analysis, skepticism toward extraordinary claims, and appreciation for the remarkable physics that governs small objects wandering between the stars. Part 9. Military and political implications, if it were a probe. In the unlikely but scientifically conceivable scenario that 3I-ATLAS represents artificial rather than natural phenomena, humanity would face its first confirmed encounter with technology of non-human origin. While current evidence strongly supports natural explanations, exploring this hypothetical scenario reveals important questions about our preparedness for genuinely extraordinary discoveries and the frameworks that might guide our response. The legal foundation for such a situation already exists, though it was written with very different scenarios in mind. The Outer Space Treaty of 1967, ratified by over 100 nations including all major space powers, establishes fundamental principles for activities beyond Earth's atmosphere. The treaty prohibits the placement of weapons of mass destruction in space and requires nations to avoid harmful contamination of celestial bodies. More relevantly, it assigns responsibility to launching states for any space objects under their jurisdiction. But what happens when the space object in question originates from outside our solar system entirely? The treaty framework assumes human actors and terrestrial politics, not cosmic visitors that predate human civilization. International legal scholars have begun examining these gaps, but no binding agreements address the discovery of extraterrestrial artifacts or the protocols that should govern our response. The SETI Institute and the International Academy of Astronautics have developed post-detection protocols for radio signals from extraterrestrial intelligence, but these guidelines focus primarily on communication scenarios rather than physical artifacts. The protocols emphasize verification through independent observation, transparency in data sharing, and international coordination before any response attempts. However, these remain non-binding recommendations rather than enforceable international law. NASA's Planetary Defense Coordination Office would likely play a central role in any response to confirmed extraterrestrial technology, even though its primary mission focuses on natural impact hazards. The office has established procedures for trajectory assessment, risk evaluation, and public communication that could adapt to artificial objects. The international collaboration networks developed for asteroid monitoring would provide ready-made frameworks for coordinating global response efforts. In the realpolitik of international relations, the discovery of extraterrestrial technology would inevitably trigger national security considerations alongside scientific ones. Major space powers might conduct passive intelligence gathering, listening for radio emissions, analyzing thermal signatures, or attempting to detect other technological signatures. However, any overt attempts to intercept or interfere with such an object would raise complex legal and diplomatic issues under existing space law. The proposals by some researchers to use existing spacecraft like Juno or Mars orbiters for closer observations of 3I-ATLAS illustrate how national assets might be retasked for international scientific purposes. Such missions would require careful coordination to ensure they're perceived as collaborative scientific endeavors rather than unilateral intelligence-gathering operations. Academic literature has explored more speculative scenarios involving potential arms races or dark forest dynamics, the possibility that contact with extraterrestrial intelligence might trigger existential competition rather than peaceful cooperation. However, these scenarios lack policy consensus and remain largely theoretical. Most experts in astrobiology, international relations, and space policy counsel extreme caution and verification before assuming hostile intentions. The communication strategy for managing public response to confirmed extraterrestrial technology would require unprecedented coordination between scientific institutions, government agencies, and international organizations. The primary goals would include avoiding panic, maintaining social stability, and ensuring that accurate information reaches the public faster than misinformation and speculation. Rapid publication of raw observational data would serve multiple purposes, enabling independent verification by scientists worldwide, demonstrating transparency in the discovery process, and providing factual foundations that could counter conspiracy theories or sensational interpretations. The success of this approach would depend heavily on media literacy and public understanding of scientific processes. If an extraterrestrial artifact began emitting signals or attempting communication, the United Nations Office for Outer Space Affairs would likely facilitate multilateral discussions while scientific teams worked to decode and understand any messages. The UN framework provides established mechanisms for international coordination, though its effectiveness would depend on the willingness of member states to subordinate national interests to collective human interests. The precedent of international cooperation in Antarctic research, governed by the Antarctic Treaty System, offers one model for how humanity might approach extraterrestrial discoveries. The Antarctic Treaty establishes the continent as a scientific preserve, prohibits military activities, and requires international cooperation in research activities. Similar principles might guide the study of confirmed extraterrestrial artifacts. However, the Antarctic model assumes a fixed location that can be claimed and controlled through territorial agreements. An interstellar visitor like 3I-ATLAS passes through our solar system on a hyperbolic trajectory, remaining accessible for only a few months before disappearing back into interstellar space. This temporal constraint would create tremendous pressure for rapid decision-making and coordination. The economic implications of confirmed extraterrestrial technology discovery could prove as significant as the political ones. Financial markets might experience extreme volatility as investors attempt to price the implications of contact with superior technology. Industries ranging from aerospace to telecommunications might face sudden obsolescence or unprecedented opportunities, depending on the nature and accessibility of any discovered technologies. Religious and philosophical communities would grapple with fundamental questions about humanity's place in creation and our relationships with other intelligent beings. The major world religions have developed various theological positions on the possibility of extraterrestrial life, but the actual confirmation of intelligent non-human technology would test these frameworks in unprecedented ways. Educational systems would face immediate demands for curricula addressing extraterrestrial contact, astrobiology, and the implications of cosmic citizenship. The generation of children growing up after confirmed contact would inhabit a fundamentally different conceptual universe than previous generations, with implications we can barely begin to imagine. Yet all of these speculative scenarios depend on a crucial premise that current evidence does not support: that 3I-ATLAS represents technology rather than natural phenomena. The carbon dioxide emissions detected by spherics, the dust morphology observed by Hubble, and the spectroscopic features identified by JWST all point toward conventional cometary activity rather than artificial systems. This thought experiment serves important functions nonetheless. By examining our preparedness for extraordinary discoveries, we identify gaps in international frameworks, communication strategies, and decision-making processes that might prove crucial in future scenarios. The next confirmed interstellar visitor might indeed challenge our assumptions about what constitutes natural versus artificial phenomena. Moreover, the exercise demonstrates the importance of maintaining both scientific rigor and institutional preparedness. We must neither dismiss extraordinary possibilities without investigation, nor accept them without extraordinary evidence. The balance between these positions will determine not just our response to 3I-ATLAS, but our readiness for the genuinely transformative discoveries that may await us among the stars. For now, 3I-ATLAS remains a remarkable natural phenomenon, a chunk of ancient ice and rock carrying chemical signatures from another stellar system, offering insights into planetary formation processes throughout the galaxy. But our careful consideration of alternative scenarios reflects the maturity of a species beginning to take seriously its place in a universe that may hold surprises beyond our current imagination. Part 10. The Coincidence Problem. Among the most intriguing aspects of 3I-ATLAS's trajectory is what some observers have termed its suspiciously orderly geometry. The object travels on a retrograde orbit, moving opposite to the direction of planetary motion, yet its path lies only approximately 5 degrees from the ecliptic plane, the imaginary disk that contains most planetary orbits. This near alignment, combined with precisely timed close encounters with major planets, creates patterns that challenge purely random explanations and invite deeper investigation. The numbers tell a remarkable story of cosmic choreography. 3I-ATLAS will pass within 0.19 to 0.20 astronomical units of Mars on October 3, 2025, roughly 28 to 30 million kilometers, closer than Mars's own moon Phobos orbits the planet. Its Jupiter encounter on March 16, 2026, brings it within 0.36 astronomical units, about 54 million kilometers, of the solar system's largest planet. Earth receives the most distant approach at approximately 1.8 astronomical units in December 2025, but even this safe distance represents a precisely calculated flyby rather than a random passage. Could such geometric precision result from intentional targeting by an advanced civilization? The question deserves serious examination, but it requires careful analysis of what we mean by coincidence in astronomical contexts, and how selection effects might influence our perceptions of significance. To evaluate whether 3I-ATLAS's planetary encounters represent genuine anomalies, we must first establish baseline expectations for random interstellar trajectories. Computer simulations can generate thousands of hypothetical hyperbolic orbits with various inclinations, orientations, and entry velocities, then calculate what percentage experience close planetary encounters purely by chance. The results of such analysis reveal that our solar system's architecture makes planetary encounters more common than intuition might suggest. Jupiter and Saturn, with their enormous gravitational spheres of influence, can deflect or capture objects from considerable distances. Mars, despite its smaller size, orbits in a region where many hyperbolic trajectories naturally converge. The statistical probability of an incoming interstellar object experiencing close encounters with multiple planets reaches levels that no longer require exotic explanations. Moreover, we must account for observational selection effects that bias our sample toward objects with interesting properties. Surveys like 3I-ATLAS are optimized to detect objects in specific regions of the sky, particularly areas near the ecliptic plane where most solar system activity occurs. An interstellar visitor with an orbital inclination far from the ecliptic might pass through our solar system completely undetected, never appearing in our astronomical catalogues. The Precovery data that extended 3I-ATLAS's observation arc back to May 2025 provides crucial constraints on any designed trajectory hypothesis. The object's path was established through multiple independent observations over several months, reducing the degrees of freedom available for fitting intentionally engineered trajectories. The more data we collect, the more difficult it becomes to argue that the trajectory was artificially constructed rather than naturally determined. The near-ecliptic inclination that initially seemed suspicious becomes less remarkable when we consider the galactic context. Interstellar objects often approach from directions related to the galaxy's disk structure, and the ecliptic plane of our solar system roughly aligns with this galactic disk. Objects streaming in from typical galactic directions will naturally tend to intersect our solar system near the ecliptic plane more often than from random directions. Furthermore, the phase angle optical effects that create 3I-ATLAS's apparent sunward glow can be fully explained through conventional dust physics without invoking artificial illumination or propulsion systems. Anti-tail phenomena occur regularly in natural comets when large dust grains, too heavy for solar wind to blow away efficiently, create structures that appear to point toward the Sun when viewed from specific geometric perspectives. However, rigorous science requires us to identify falsifiable predictions that could distinguish between natural and artificial explanations. If 3I-ATLAS were indeed a probe or artifact, we might expect to observe specific signatures that natural objects cannot produce: stable, narrowband spectral emissions characteristic of artificial energy sources; structured, repetitive radio signals indicating communication or navigation systems; non-Keplerian motion patterns suggesting controlled propulsion or course corrections. To date, no observations have detected any such signatures. The radio spectrum around 3I-ATLAS shows only the background noise typical of space environments. Its motion follows gravitational predictions with the precision expected from celestial mechanics. Its spectroscopic signatures match those of sublimating cometary ices rather than exotic energy sources or manufactured materials. The human tendency toward apophenia, perceiving meaningful patterns in random data, provides an important psychological context for evaluating apparent coincidences. Our brains evolved in environments where pattern recognition offered survival advantages, leading us to identify meaningful relationships even in genuinely random phenomena. When confronted with rare cosmic events, we naturally seek explanations that involve intention, design, or significance, rather than acknowledging the role of pure chance. This tendency becomes particularly pronounced when dealing with events that occur on astronomical scales and timelines that exceed normal human experience. The idea that an interstellar object could wander the galaxy for millions of years, then happen to pass through our solar system during the brief period when human civilization has developed the technology to observe it, can feel almost impossibly coincidental. Yet the vast scales involved make such apparent coincidences statistically inevitable over cosmic timescales. The Monte Carlo simulations that can test these intuitions reveal fascinating insights about orbital dynamics and probability. By generating thousands of random hyperbolic trajectories and calculating their planetary encounter statistics, we can determine what percentage would experience close approaches comparable to 3I-ATLAS's encounters. The results typically show that such encounters occur with sufficient frequency to require no special explanation. More sophisticated analysis can examine correlations between different orbital elements, whether objects with specific inclinations tend to have particular encounter geometries, or whether certain entry velocities predispose visitors to multiple planetary flybys. These studies help distinguish between genuinely anomalous properties and the natural consequences of gravitational dynamics in multi-body systems. The upcoming Mars encounter in October 2025 offers an excellent opportunity to test various hypotheses about 3I-ATLAS's nature. If the object were artificial, we might expect its trajectory to show subtle adjustments during the Mars flyby, course corrections that optimize its subsequent Jupiter encounter or adjust its departure trajectory. Natural objects, by contrast, should follow purely gravitational paths determined by their masses and velocities. High-resolution observations during the Mars encounter might also reveal structural details invisible from greater distances. Artificial objects could display geometric regularity, surface features inconsistent with natural erosion processes, or thermal signatures indicating internal energy sources. Natural comets should show irregular shapes, impact craters, and thermal emissions consistent with solar heating of volatile rich surfaces. The broader lesson from examining 3I-ATLAS's apparent coincidences is that extraordinary claims require extraordinary evidence, but they also require extraordinary care in distinguishing between genuine anomalies and the normal products of selection effects, statistical flukes, and human pattern-seeking behaviors. The universe is under no obligation to behave in ways that match our intuitions about probability and significance. Whether 3I-ATLAS represents a remarkable natural phenomenon or something far more extraordinary, its study demonstrates the importance of quantitative analysis in evaluating apparent coincidences. Only by calculating actual probabilities, accounting for selection effects, and testing specific predictions can we distinguish between meaningful patterns and cosmic chance. The answer to the coincidence problem may ultimately lie not in the stars, but in our growing sophistication as a species capable of rigorous statistical thinking about astronomical phenomena that challenge our everyday understanding of probability, causation, and significance. Part 11. Exotic physics, or just exotic ice. As we delve deeper into the scientific mystery of 3I-ATLAS, we encounter a fundamental question that has driven astronomy for centuries. When confronted with unusual observations, should we invoke exotic new physics or explore whether familiar physics operating in unfamiliar conditions can explain what we see? The history of science suggests that mundane explanations, carefully analyzed, often prove more illuminating than speculative alternatives, though occasionally, genuinely revolutionary discoveries emerge from apparent anomalies. The natural explanations for 3I-ATLAS's behavior begin with its composition, which appears dominated by carbon dioxide-rich ices that sublimate readily as the object approaches our Sunday. This carbon dioxide dominance at large heliocentric distances perfectly matches theoretical predictions for objects that formed in extremely cold environments and spent millions of years in interstellar space, where only the most volatile compounds remain easily sublimable. The FIREX mission's detection of an extended carbon dioxide cloud spanning hundreds of thousands of kilometers provides direct observational evidence for this sublimation process. As solar radiation warms 3I-ATLAS's surface, solid carbon dioxide transitions directly from ice to gas, creating the expanding coma we observe. The James Webb Space Telescope's spectroscopic confirmation of these carbon dioxide features adds independent verification to this straightforward physical explanation. Water signatures remain weaker in current observations, but this pattern aligns perfectly with sublimation physics. Water ice requires higher temperatures than carbon dioxide to transition from solid to gas, so we expect water vapor emissions to strengthen as 3I-ATLAS approaches its late October perihelion. This represents a testable prediction. If 3I-ATLAS follows natural cometry physics, water signatures should become more prominent in spectroscopic observations as solar heating intensifies. The intriguing possibility of radiolysis processed hydrogen provides another natural explanation that draws parallels to the Oumuamua mystery. Over geological timescales in interstellar space, cosmic radiation can break down water-ice molecules, creating trapped hydrogen gas within the object's interior structure. When solar heating warms the surface, this hydrogen can escape in quantities too small to create visible outgassing but sufficient to produce subtle dynamical effects. This radiolysis model successfully explained Oumuamua's mysterious acceleration without requiring artificial propulsion systems. While 3I-ATLAS shows clear evidence of visible outgassing that makes such invisible acceleration unnecessary, the underlying physics demonstrates how seemingly exotic behavior can result from well-understood processes operating over cosmic timescales. Grain physics offers another avenue for natural explanations of 3I-ATLAS's unusual brightness distribution. Large dust particles near the nucleus can create complex optical effects when illuminated by solar radiation. Depending on particle sizes, compositions, and spatial distributions, dust clouds can produce brightness concentrations that appear to point toward the sun. the apparent forward glow that initially attracted attention as potentially artificial. These anti-tail phenomena are well documented in solar system comets, where radiation pressure and gravitational forces create intricate dust structures that can produce counterintuitive appearances when viewed from specific geometric perspectives. No exotic physics or artificial illumination is required to explain such features, just the complex interplay between dust dynamics, radiation pressure, and orbital mechanics. The question of 3I-ATLAS's ultimate origin adds another layer of natural complexity to consider. Different research teams have proposed origins in either the galaxy's thin disk or thick disk, stellar populations with different ages, metallicities, and kinematic properties. These different environments would subject forming objects to different thermal histories, cosmic ray exposure levels, and chemical processing conditions. Thin disk origins might suggest a relatively young object formed around a metal-rich star similar to our Sun, while thick disk origins could indicate an ancient wanderer that predates our solar system's formation. The compositional clues that might discriminate between these scenarios remain uncertain, but they illustrate how natural astrophysical processes can produce objects with exotic properties through perfectly conventional physics. Recent orbital analysis published in Astronomy and Astrophysics has refined 3I-ATLAS's trajectory calculations, confirming its extreme hyperbolicity in barycentric coordinates, measurements relative to the solar system's center of mass rather than the Sun alone. This analysis underscores the object's genuinely interstellar pedigree while providing increasingly precise predictions for its future motion. The concept of unknown astrophysical processes deserves careful consideration in any complete analysis. Our understanding of cometary physics, interstellar chemistry, and small body evolution continues to evolve as new observations challenge existing models. 3I-ATLAS might exhibit behavior that requires refinements to current theory without necessarily invoking artificial explanations. However, the scientific principle of Occam's razor suggests we should exhaust natural explanations before considering more exotic alternatives. Unknown natural processes, while possible, represent less radical departures from established science than the conclusion that we're observing alien technology. The burden of proof for extraordinary claims rests with those proposing them, not with those defending conventional interpretations. This burden of proof framework helps establish clear criteria for evaluating future observations of 3I-ATLAS. If natural cometary processes explain the object's behavior, we should continue to observe spectroscopic signatures consistent with sublimating volatiles, morphological features that match dust and gas dynamics, and thermal emissions that correlate with solar heating patterns. Conversely, artificial explanations would predict very different observational signatures, engineered materials in spectroscopic analysis, geometric structures inconsistent with natural erosion processes, energy emissions that exceed solar heating contributions, or controlled trajectory modifications that violate purely gravitational motion. The peer review process will play a crucial role in evaluating any anomalous findings as they emerge. Extraordinary claims about 3I-ATLAS's nature will face intense scrutiny from the international astronomical community, requiring independent confirmation and thorough analysis before gaining acceptance. This process serves as an essential filter between preliminary observations and established conclusions. As 3I-ATLAS continues its approach toward perihelion, we can make specific predictions based on natural physics that remain testable through ongoing observations. The carbon dioxide emissions should continue following patterns dictated by solar heating and sublimation thermodynamics. Water vapor signatures should strengthen as surface temperatures rise. Dust production should increase as thermal stresses liberate more material from the nucleus surface. Any significant deviations from these predictions would warrant careful investigation and potentially challenge natural explanations. Science progresses through such tests of competing hypotheses, where observations serve as arbitrators between different theoretical frameworks. The exotic ice hypothesis, that 3I-ATLAS represents a natural but compositionally unusual object processed by millions of years of interstellar wandering, currently provides the most comprehensive explanation for all observed properties. This interpretation requires no physics beyond our current understanding, makes testable predictions about future observations, and aligns with comparative studies of other interstellar visitors. Yet science demands intellectual humility about the limits of current knowledge. If 3I-ATLAS ultimately reveals properties that challenge natural explanations despite our best efforts to understand them through conventional physics, we must remain open to genuinely revolutionary discoveries. The universe has surprised us before with phenomena that initially seemed impossible but ultimately expanded our understanding of natural processes. Whether 3I-ATLAS proves to be exotic ice or something far stranger, its study exemplifies the scientific method at work: careful observation, rigorous analysis, and willingness to follow evidence wherever it leads, while maintaining appropriate skepticism toward conclusions that would revolutionize our understanding of the cosmos. Part 12. The first contact stress test. In the realm of scientific thought experiments, few scenarios capture the imagination quite like first contact with extraterrestrial intelligence. While 3I-ATLAS shows no signs of artificial origin or communication attempts, exploring how humanity might respond to such a discovery reveals critical gaps in our preparedness for potentially transformative cosmic encounters. Consider this scenario. Tomorrow morning, radio telescopes detect a structured, clearly artificial signal emanating from 3I-ATLAS's position. What happens next? The first hours would test every protocol humanity has developed for managing extraordinary discoveries. According to SETI post-detection principles established by the International Academy of Astronautics, the detecting observatory would immediately begin verification procedures, confirming the signal's reality through multiple independent observations and ruling out terrestrial interference, equipment malfunction, or natural phenomena that might mimic artificial transmissions. These verification steps, mundane as they might seem, would prove crucial in preventing false alarms that could trigger premature public panic or inappropriate government responses. The scientific community learned hard lessons from past incidents involving pulsars initially mistaken for alien beacons and fast radio bursts that seemed too structured to be natural. Extraordinary claims about extraterrestrial contact demand extraordinary verification before public announcement. Simultaneously, the detecting institution would notify key international organizations according to established protocols. The International Astronomical Union serves as the primary coordinating body for astronomical discoveries, while the United Nations Office for Outer Space Affairs provides frameworks for international cooperation in space-related matters. Both organizations maintain contact lists and communication procedures designed for rapid dissemination of critical information. The Outer Space Treaty of 1967, despite being written decades before SETI became a serious scientific discipline, establishes principles that would guide international responses to confirmed extraterrestrial contact. The treaty's emphasis on peaceful uses of outer space, avoidance of harmful contamination, and international cooperation provides a legal foundation for coordinated response efforts. NASA's Planetary Defense Coordination Office, despite its primary focus on natural impact hazards, would likely assume a central role in managing public communications about any confirmed alien contact. The office has established procedures for risk assessment, trajectory analysis, and public messaging that could adapt to communication scenarios. The key difference would be managing not physical danger, but the psychological and social impacts of confirmed contact with non-human intelligence. National security agencies worldwide would inevitably become involved in any confirmed contact scenario, though the balance between security concerns and scientific transparency would prove delicate. Intelligence services might attempt to detect additional signals, analyze transmission characteristics for technological insights, or assess potential threats to national interests. However, the international nature of astronomical research and the global implications of contact would pressure governments toward transparency and cooperation rather than unilateral secrecy. The existing Mars orbital assets and Jupiter mission that some researchers have suggested for studying 3I-ATLAS would face immediate retasking pressure if the object began signaling. Spacecraft already positioned near the object could potentially serve as relay stations, signal amplifiers, or close-range observation platforms. However, the technical feasibility of such operations would depend heavily on orbital mechanics, communication capabilities, and the specific characteristics of any detected signals. The Rio scale and San Marino scale, developed by SETI researchers to quantify the significance and implications of potential extraterrestrial contact, would provide frameworks for assessing the importance of any signals from 3I-ATLAS. These scales consider factors such as signal verification confidence, information content, and potential societal impact, helping officials communicate the significance of discoveries to both scientific communities and general public. Perhaps the most challenging aspect of confirmed contact would be the question of response. Who, if anyone, speaks for humanity? Current international frameworks lack binding agreements on this fundamental question. The SETI post-detection protocols recommend against any response transmissions until thorough international consultation occurs, but these guidelines carry no legal authority and might prove difficult to enforce in practice. The democratic deficit in cosmic communication protocols reflects broader challenges in global governance. While the United Nations provides forums for international cooperation, its consensus-building processes might prove too slow for scenarios involving time-sensitive communication opportunities. The brief window during which 3I-ATLAS remains accessible to our solar system would create tremendous pressure for rapid decision-making. Media management would represent another critical challenge requiring unprecedented coordination between scientific institutions, government agencies, and international organizations. The primary goals would include preventing panic, countering misinformation, and ensuring accurate information reaches the public faster than speculation and conspiracy theories. The success of this effort would depend largely on public trust in institutions and widespread media literacy. Rapid publication of raw observational data would serve multiple crucial functions in any contact scenario. Open data policies would enable independent verification by scientists worldwide, demonstrate transparency in the discovery process, and provide factual foundations for public understanding. The precedent of immediate data sharing for gravitational wave detections and other major astronomical discoveries shows this approach can work effectively. Economic markets would likely experience extreme volatility as investors attempted to assess the implications of confirmed extraterrestrial contact. Financial systems built on assumptions of terrestrial isolation might face fundamental challenges. Industries ranging from telecommunications to aerospace could experience sudden obsolescence or unprecedented opportunities, depending on the nature and content of any alien communications. Religious and philosophical communities would confront perhaps the most profound implications of confirmed contact. While major world religions have developed various theological positions on extraterrestrial life, actual confirmation would test these frameworks in unprecedented ways. Educational systems would face immediate pressure to develop curricula addressing cosmic citizenship and humanity's place in a populated universe. The generational impact of confirmed contact cannot be overstated. Children growing up after such a discovery would inhabit a fundamentally different conceptual universe than previous generations. Their worldview would be shaped from birth by the knowledge that intelligence exists beyond Earth, with implications for everything from career choices to philosophical perspectives that we can barely begin to imagine. Technical analysis of any signals would proceed along well-established SETI protocols, looking for evidence of information content, technological sophistication, and intentional communication versus natural phenomena. The characteristics of signals, their frequency, modulation, information density, and temporal patterns could provide insights into the transmitting civilization's technology level and intentions. However, we must emphasize the crucial reality check that threads through this entire thought experiment. 3I-ATLAS shows no signs of signaling or artificial origin. Current observations reveal carbon dioxide emissions, natural dust morphology, and behavioral patterns consistent with cometary physics. This scenario represents a preparedness exercise rather than a prediction based on actual evidence. The value of such exercises lies in identifying gaps in our institutional frameworks, communication strategies, and international cooperation mechanisms. By thinking through these scenarios before they become reality, we can develop better protocols for managing genuinely extraordinary discoveries when they eventually occur. Moreover, this exercise highlights the importance of maintaining both scientific rigor and institutional preparedness. We must neither dismiss extraordinary possibilities without proper investigation, nor accept them without extraordinary evidence. The balance between these positions will determine not just our response to potential signals from 3I-ATLAS, but our readiness for the genuinely transformative discoveries that may await us among the stars. The stress test reveals that while humanity possesses many of the institutional building blocks needed for managing extraterrestrial contact, significant gaps remain in international coordination, democratic participation, and public communication. These gaps reflect broader challenges in global governance that extend far beyond SETI scenarios. Perhaps most importantly, this thought experiment demonstrates why the scientific community's measured, evidence-based approach to studying 3I-ATLAS serves humanity's long-term interests. By establishing clear standards for evaluating extraordinary claims, maintaining transparency in research processes, and building international cooperation around shared scientific goals, we create foundations for wisdom in responding to whatever discoveries the universe may reveal. Whether 3I-ATLAS ultimately proves to be remarkable natural phenomena or reveals unexpected properties, our careful preparation for extraordinary possibilities reflects the growing maturity of a species beginning to take seriously its responsibilities as cosmic citizens in a universe that may hold surprises beyond our current imagination. Part 13. The Great Filter Question. The possibility, however remote, that interstellar objects like 3I-ATLAS might represent artifacts of alien civilizations forces us to confront one of the most profound questions in astrobiology. If we ever do discover evidence of extraterrestrial technology, what would it tell us about the fate of intelligence in the universe? The answer to this question touches on one of the most sobering concepts in modern science, the Great Filter hypothesis, and could fundamentally reshape our understanding of humanity's cosmic future. The Great Filter represents a theoretical explanation for the Fermi paradox, the apparent contradiction between the high probability of extraterrestrial civilizations and our complete lack of evidence for them. According to this hypothesis, there exists some incredibly difficult evolutionary step that prevents most life from reaching technological maturity. The filter might lie behind us, in which case we're extraordinarily fortunate to have passed through it. Or it might lie ahead of us, suggesting that technological civilizations typically destroy themselves before spreading throughout the galaxy. If interstellar probes like 3I-ATLAS actually represented remnants of extinct civilizations, they would provide sobering evidence that the Great Filter lies in our future rather than our past. Advanced species might regularly develop the technology needed to explore other stellar systems, only to succumb to technological self-destruction, environmental collapse, or other existential risks before establishing permanent galactic presence. Dr. A.V. Loeb and other researchers have argued that discovering alien artifacts would fundamentally reset humanity's priorities regarding space exploration, existential risk mitigation, and long-term survival strategies. If other civilizations have risen and fallen throughout galactic history, leaving only scattered technological debris as evidence of their existence, it would suggest that technological intelligence faces systematic challenges that we have yet to understand or overcome. However, critics note that this interpretation requires accepting extraordinary claims without extraordinary evidence. The absence of confirmed alien artifacts means we're still operating in the realm of speculation rather than established fact. Natural explanations for interstellar objects like 3I-ATLAS, Oumuamua, and Borisov remain more consistent with current observations than hypotheses involving alien technology. The natural interpretation of these visitors already provides profound insights into cosmic processes and planetary formation throughout the galaxy. Borisov's familiar chemistry demonstrated that the basic physics of planet formation, the accretion of ice and rock around young stars, operates similarly across different stellar systems. 3I-ATLAS's carbon dioxide-rich composition adds to this picture, showing how different stellar environments can produce objects with varying volatile content. This growing catalogue of interstellar visitors offers a unique window into planetary science beyond our solar system. Each object carries chemical fingerprints that reveal conditions around its birth star, isotopic ratios that constrain formation timescales, and structural properties that illuminate billions of years of thermal and dynamical evolution. These insights advance our understanding of galactic ecology without requiring exotic explanations. Yet the possibility of technological artifacts among interstellar populations raises important questions about detection methods and statistical analysis. A galaxy filled with natural interstellar debris could effectively camouflage artificial objects, making them difficult to identify through conventional astronomical observations. This possibility emphasizes the importance of developing instrumental signatures that could distinguish manufactured materials from natural compositions. The search for such signatures parallels efforts in SETI research to identify artificial signals against the background of natural cosmic radio emissions. Just as radio astronomy has developed sophisticated techniques for recognizing structured transmissions, optical and infrared astronomy might need to develop new methods for identifying technological materials, geometric regularity, or energy sources inconsistent with natural processes. The philosophical implications extend beyond questions of detection to fundamental issues about intelligence and cosmic evolution. If technological civilizations regularly emerge throughout the galaxy only to face systematic existential risks, it would suggest that intelligence itself might be a maladaptive evolutionary strategy on cosmic timescales. The same cognitive capabilities that enable tool use, scientific discovery, and space exploration might also predispose species towards self-destructive behaviors. Alternatively, discovering evidence of successful long-lived civilizations would provide encouraging evidence that technological species can overcome existential risks and establish sustainable galactic presence. Such discoveries might offer insights into successful survival strategies, technological development paths, or social institutions that promote long-term stability. The timescales involved in these scenarios dwarf human historical experience. Galactic rotation periods span hundreds of millions of years, stellar lifetimes extend across billions of years, and the universe itself has existed for nearly 14 billion years. Any technological artifacts we might discover could represent civilizations that arose and vanished long before Earth's biosphere developed complex life forms. This temporal perspective highlights both the rarity and significance of the current moment in cosmic history. Humanity has existed for only a fraction of the universe's lifetime, yet we've already developed the technology needed to detect and study interstellar visitors. Whether we represent typical or atypical evolutionary outcomes remains one of the great unknowns in astrobiology. The rapidly improving capabilities of astronomical surveys promise to revolutionize our understanding of interstellar object populations within the next decade. The Vera Rubin Observatory's legacy survey of space and time will detect hundreds or potentially thousands of interstellar visitors each year, providing statistical samples large enough to identify systematic patterns and anomalies. This statistical approach offers the best hope for resolving questions about the prevalence of natural versus artificial objects among interstellar populations. Rare technological artifacts might become identifiable through systematic deviations from the distributions expected for natural populations. Alternatively, Comprehensive studies might definitively establish that all interstellar objects follow natural formation and evolution processes. Even negative results, finding no evidence of alien technology among large samples of interstellar objects, would provide valuable information for astrobiology and SETI research. Such results would help constrain models of technological civilization prevalence, suggest that artifact-producing species are rarer than optimistic estimates predict, or indicate that advanced civilizations employ technologies that remain undetectable through our current methods. The existential significance of these questions extends far beyond academic curiosity. If humanity represents a typical technological species, our fate might parallel that of countless other civilizations throughout galactic history. Understanding the challenges that other species have faced and potentially overcome could inform our own approaches to long-term survival and cosmic expansion. The concept of cosmic loneliness versus cosmic community profoundly shapes human perspectives on meaning, purpose, and responsibility. A universe populated by technological species would offer possibilities for communication, collaboration, and shared exploration of cosmic mysteries. A universe where technological intelligence regularly emerges only to self-destruct would suggest that consciousness itself faces systematic existential challenges. For now, objects like 3I-ATLAS continue to provide insights into natural cosmic processes while challenging our assumptions about what constitutes typical versus anomalous behavior in interstellar populations. Whether future discoveries reveal evidence of alien technology or confirm that we're studying natural phenomena, the investigation itself exemplifies humanity's growing capacity for rigorous scientific inquiry into questions that touch the deepest levels of cosmic significance. The Great Filter question ultimately remains open, awaiting evidence that may emerge from careful study of interstellar visitors, radio searches for technological signatures, or direct exploration of nearby stellar systems. Until then, we continue to examine each cosmic messenger with the scientific rigor and philosophical humility appropriate to species seeking to understand their place in a universe that may hold surprises beyond our current imagination. Part 14. Wonder over Fear. As we near the end of our journey through the scientific mystery of 3I-ATLAS, it's time to step back and examine the evidence with the clarity that comes from comprehensive analysis. When we compile observations from Hubble's morphological studies, JWST's spectroscopic investigations, and SphereX's compositional mapping, a consistent picture emerges. We are studying a remarkable natural comet carrying volatile-rich ice and dust from another stellar system. The carbon dioxide and water vapor detections provide unambiguous evidence of active sublimation processes that require no exotic explanations. The teardrop-shaped dust coma, revealed by Hubble imaging, matches theoretical models of cometary activity with extraordinary precision. The nucleus size constraints, measuring between 0.32 and 5.6 kilometers in diameter, align perfectly with expectations for objects that could preserve volatile ices during millions of years of interstellar wandering. This convergence of independent observations demonstrates science at its most powerful, multiple instruments, operated by different teams, using distinct methodologies, all reaching compatible conclusions about 3I-ATLAS's fundamental nature. No single observation by itself would prove definitive, but the cumulative weight of evidence builds a compelling case for natural rather than artificial origins. The contrast between journalism's need for novelty and science's commitment to accuracy illuminates why preliminary speculations about alien technology gained such prominence in early coverage. News cycles demand fresh angles and dramatic narratives, often emphasizing the most exotic possible explanations before peer review and archival recovery data can provide more prosaic conclusions. This tension between media timescales and scientific timescales reflects a fundamental challenge in communicating about cosmic discoveries. The most accurate information emerges slowly through careful analysis, cross-validation, and peer review, while public interest peaks immediately following initial discovery announcements. By the time definitive conclusions emerge, attention has often shifted to newer mysteries. The international collaboration that has characterized 3I-ATLAS research demonstrates humanity's remarkable capacity for cooperation when confronted with genuine cosmic mysteries. The Minor Planet Center coordinated global observations within hours of discovery. NASA and ESA shared telescope time and data without institutional barriers. University teams worldwide contributed specialized expertise in orbital dynamics, spectroscopy, and compositional analysis. This collaborative spirit transcends the political divisions that often dominate terrestrial affairs, suggesting that cosmic encounters might serve as catalysts for broader international cooperation. When faced with phenomena that dwarf human timescales and challenge terrestrial perspectives, our species demonstrates an inspiring capacity for collective scientific endeavor. The educational implications of 3I-ATLAS's study extend far beyond astronomical knowledge. The object's carbon dioxide-dominated composition teaches us about volatile survival in interstellar environments, planetary formation processes around other stars, and the chemical diversity that exists throughout our galactic neighborhood. These insights advance our understanding of cosmic chemistry while providing tangible connections between abstract astrophysical theories and observable phenomena. The sophisticated toolchain that has enabled real-time analysis of 3I-ATLAS represents decades of investment in space-based astronomy. Hubble's optical imaging capabilities, developed over 30 years of orbital operations, provide morphological insights impossible from ground-based telescopes. JWST's infrared spectroscopy, representing cutting-edge detector technology and precision pointing systems, identifies molecular species with unprecedented sensitivity. SphereX's wide-field mapping capabilities reveal extended structures that single-pointing observations might miss entirely. This instrumental ecosystem exemplifies how long-term scientific investments pay dividends in unexpected ways. Telescopes designed for studying distant galaxies and exoplanet atmospheres adapt seamlessly to analyzing interstellar visitors, demonstrating the interconnected nature of astronomical research and the value of maintaining diverse observational capabilities. For amateur astronomers and citizen scientists, 3I-ATLAS offers observing opportunities that connect backyard telescopes with cutting-edge research. While the object remains too faint for easy detection without specialized equipment, experienced observers with larger telescopes and sensitive cameras might capture images during favorable viewing windows. These observations contribute to the global monitoring effort while providing personal connections to genuine cosmic exploration. The mission concepts that have emerged for closer study of 3I-ATLAS, potential observations by Juno during the Jupiter encounter or Mars orbiters during the October flyby, illustrate how existing space assets can be repurposed for new scientific objectives. These proposals demonstrate the flexibility of modern spacecraft operations while highlighting the importance of rapid response capabilities for studying transient phenomena. However, the real significance of these mission concepts lies not in their technical feasibility, but in their demonstration of humanity's growing sophistication in cosmic exploration. We now routinely operate spacecraft throughout the solar system, maintain communication networks across interplanetary distances, and coordinate complex observation campaigns involving multiple space and ground-based assets. The cultural transformation represented by our response to 3I-ATLAS deserves recognition alongside the scientific achievements. Instead of interpreting this cosmic visitor as an omen of disaster or divine judgment, we've approached it as an opportunity for learning and discovery. This shift from fear-based to curiosity-based responses to celestial events represents genuine progress in human intellectual development. The process transparency that has characterized 3I-ATLAS research, with observations, data, and analysis freely shared through international databases, demonstrates how open science accelerates understanding while building public trust. Citizens can examine the same orbital data, spectroscopic measurements, and imaging results that professional astronomers use in their research, participating directly in the process of cosmic discovery. This democratization of astronomical data creates educational opportunities that previous generations could never have imagined. Students can download real observational data, perform their own analysis, and reach independent conclusions about cosmic phenomena. The gap between professional research and public engagement continues to shrink as data access improves and analysis tools become more accessible. Looking toward the future, 3I-ATLAS provides a template for how humanity might approach subsequent interstellar visitors. The rapid response protocols developed for this object, the international coordination mechanisms, and the multi-instrument observation strategies will serve as models for studying future cosmic messengers. Each encounter teaches us not just about individual objects, but about how to conduct effective astronomical research in an era of increasing discovery rates. The upcoming observation windows, 3I-ATLAS's October perihelion passage and its December closest approach to Earth, offer final opportunities to test our understanding against direct measurements. If the natural comet hypothesis proves correct, we should observe increased water vapor emissions, enhanced dust production, and morphological changes consistent with intensifying solar heating. These predictions provide clear benchmarks for validating our current understanding. Whether these predictions prove accurate or reveal unexpected surprises, the investigation of 3I-ATLAS exemplifies the scientific method applied to cosmic mysteries: careful observation, hypothesis testing, international collaboration, and willingness to be surprised by what the universe reveals. This approach serves humanity's long-term interests better than either premature acceptance of extraordinary claims or reflexive dismissal of unusual observations. The legacy of 3I-ATLAS will ultimately be determined not by whether it proves exotic or mundane, but by how well its study advances our understanding of interstellar objects, improves our capabilities for cosmic exploration, and demonstrates our growing maturity as a species capable of rigorous scientific inquiry into the deepest questions about our place in the universe. As this remarkable visitor continues its journey toward the outer solar system, it carries with it our hopes for continued cosmic discovery, our appreciation for the elegant physics that governs celestial mechanics, and our growing confidence in humanity's ability to respond to cosmic mysteries with wisdom rather than fear. Part 15. Our Place in the Cosmos. In the end, 3I-ATLAS forces us to confront a profound truth about our cosmic situation. We are a young species, barely a few 100,000 years old, watching chunks of ancient starlight and primordial ice drift past our tiny oasis in an ocean of space and time that spans billions of years and trillions of kilometers. This perspective, humbling as it may be, represents one of humanity's greatest intellectual achievements: the ability to understand our place in a universe far grander than our ancestors ever imagined. Even if 3I-ATLAS proves to be merely a natural comet, the quotation marks around that word reveal the poverty of such thinking. There is nothing mere about material that formed around another star, survived millions of years wandering the interstellar void, and now graces our telescopes with chemical signatures that reveal processes occurring billions of years ago in stellar environments we may never visit. The carbon dioxide and water vapor we detect today began their cosmic journey when the universe itself was younger, when different stars illuminated the galaxy, when Earth's biosphere was radically different from the world we inhabit. This temporal perspective transforms our understanding of what constitutes extraordinary versus ordinary phenomena. By cosmic standards, the emergence of technological civilization on Earth represents an event far more remarkable than the passage of interstellar debris through our solar system. Intelligence capable of building telescopes, launching spacecraft, and deciphering the chemical composition of objects from other stellar systems has emerged only recently in cosmic history, and perhaps only rarely throughout the galaxy. If future observations somehow revealed that 3I-ATLAS represents technology rather than natural ice, a possibility that current evidence does not support, but that scientific honesty requires us to acknowledge, humanity would face the most profound paradigm shift in our species' intellectual history. We would need to reimagine our cosmic context, our long-term survival strategies, and our responsibilities as members of a universe populated by intelligence. Such a discovery would immediately activate the international treaties, coordination protocols, and communication frameworks we examined earlier in our investigation. More importantly, it would test our wisdom, our capacity for cooperation, and our ability to respond to cosmic-scale challenges with appropriate gravity and care. But the reality check that threads through all such speculation remains clear. Earth will pass no closer than approximately 1.8 astronomical units from 3I-ATLAS in December 2025. At its closest approach, this visitor will remain about 270 million kilometers away, roughly the distance between Earth and Mars at their closest approach. We face no physical danger from this object, regardless of its ultimate nature or composition. The safety assurance allows us to approach 3I-ATLAS with pure scientific curiosity rather than existential anxiety. We can study this visitor as we would any other cosmic phenomenon, seeking to understand its properties, origins, and behavior without the urgency that might cloud our judgment if it posed actual threats to our planet or civilization. This luxury of dispassionate analysis represents a triumph of human intellectual development. Our ancestors interpreted comets as harbingers of doom precisely because they lacked the scientific frameworks needed to assess actual risks versus imagined dangers. We possess those frameworks today, along with the technological capabilities needed to track, study, and understand cosmic visitors with unprecedented precision. The humility enforced by cosmic perspective serves important functions beyond mere intellectual honesty. The recognition that our understanding remains incomplete, that surprises await us among the stars, and that the universe operates according to physical laws rather than human preferences, helps calibrate our expectations and responses to cosmic discoveries. Our experience with previous interstellar visitors, the enigmatic Oumuamua with its unusual acceleration, and the well-behaved Borisov with its textbook cometary properties, demonstrates that interstellar objects don't conform to single templates or predictable patterns. Each visitor tells its own story about stellar environments, planetary formation processes, and the complex physics that governs small body evolution over galactic timescales. 3I-ATLAS adds another chapter to this growing library of interstellar narratives. Its carbon dioxide-rich composition, high velocity, and precisely choreographed planetary encounters provide new data points for understanding how objects form around other stars, survive interstellar journeys, and interact with stellar systems they encounter during their cosmic wandering. The instrumental advances that have enabled real-time analysis of 3I-ATLAS, from Hubble's morphological imaging to JWST's molecular spectroscopy to SphereX's extended coma mapping, represent templates for studying future interstellar visitors. The next object discovered by the Vera Rubin Observatory's Legacy Survey of Space and Time will benefit from techniques, protocols, and international coordination mechanisms developed through our investigation of 3I-ATLAS. This technological and methodological progress exemplifies humanity's growing sophistication in cosmic exploration. We no longer simply observe celestial events as passive spectators. We actively investigate them using instruments that can measure chemical compositions across interstellar distances, track trajectories with extraordinary precision, and coordinate global research campaigns within hours of discovery. The civic lessons embedded in 3I-ATLAS research extend far beyond astronomical education. The ability to distinguish established facts from preliminary speculation, to appreciate uncertainty without succumbing to anxiety, and to evaluate extraordinary claims against appropriate standards of evidence serves citizens well in many contexts beyond cosmic mysteries. The media literacy skills required to navigate coverage of astronomical discoveries, recognizing the difference between peer-reviewed analysis and sensational speculation, understanding how scientific confidence evolves over time, appreciating the difference between uncertainty and danger, transfer directly to other domains where scientific information intersects with public policy and personal decision-making. Perhaps most importantly, 3I-ATLAS challenges us to expand our temporal and spatial perspectives beyond the narrow confines of human experience. The object we're studying has traveled farther than human civilization has existed, carrying materials older than complex life on Earth. Following gravitational laws that operate with mathematical precision across cosmic scales that dwarf terrestrial geography. This expansion of perspective serves as an antidote to the parochialism that often characterizes human affairs. Political disputes that seem monumental from terrestrial viewpoints shrink to appropriate proportions when viewed against cosmic timescales. International boundaries that divide our species become invisible when viewed from the perspective of an object that has wandered between stellar systems for millions of years. The call to wonder that 3I-ATLAS represents extends beyond scientific curiosity to encompass our collective response to the magnificent complexity of the universe we inhabit. The carbon dioxide-rich coma surrounding a kilometer-scale nucleus represents simple physics in action, the direct transition of solid ice to gas as stellar radiation warms ancient volatile materials. Yet this simple physics carries profound implications for understanding planetary formation throughout the galaxy, chemical processing in interstellar environments, and the cosmic ecology that connects stellar systems across vast distances and timescales. The ordinary processes of sublimation and dust dynamics operating on an extraordinary visitor from interstellar space provide insights into cosmic processes that span galactic scales. The image that will remain with us as 3I-ATLAS completes its solar system passage, a strand of carbon dioxide illuminated dust surrounding a tiny nucleus carrying chemical signatures from another star, encapsulates both the simplicity and profundity of cosmic processes. This visitor represents neither omen nor artifact, but something perhaps more remarkable: direct physical evidence of the chemical and dynamical processes that shape our galaxy. Our response to this cosmic messenger will be remembered not for the fears it failed to justify or the exotic explanations it failed to support, but for the scientific collaboration it inspired, the international cooperation it demonstrated, and the expansion of perspective it offered to anyone willing to contemplate their place in a universe far grander and more wonderful than our terrestrial experience might suggest. Fear narrows our world, reducing cosmic mysteries to threats and closing our minds to possibilities that exceed our current understanding. Wonder enlarges our world, opening our minds to the magnificent complexity of a universe that continues to surprise, educate, and inspire those brave enough to look up at the night sky and ask what secrets might be hidden among the stars. 3I-ATLAS, racing through our solar system at 200,000 kilometers per hour while carrying news from distant suns, invites us to choose wonder over fear, curiosity over anxiety, and cosmic perspective over terrestrial parochialism. Whether we accept that invitation will determine not just our understanding of this particular visitor, but our readiness for the cosmic discoveries that await us in the decades and centuries ahead.